So thank you. I'm gonna try and go for about 15 minutes or so. And my guess is that, and so in organizing this conference, Brian asked me to talk about some of the modeling activities that I've done with some students here at Drake University. Part of that was trying to locate reasonable data to kind of validate what we were doing. And so in this talk, I'm going to kind of start by describing what that actual modeling activity was. And there's also a SIMIODE resource that accompanies that. And then talk about some other examples and other resources that I've used in these last couple of years and some of the research that I've done with some undergraduate students here at Drake. And so to start off, I want to, let's see, I can't, oh, 1 second, it doesn't seem, oh, there we go, there we go. All right, so to start off, I want to talk about, I guess, kind of the motivation for how I got into this business of mathematical modeling. So my original research areas in numerical partial differential equations as it relates to shallow water wave theory, which did not bode very well with students' interest in getting engaged with mathematical research. And so we have these Friday afternoon research seminars at Drake that started back in the fall of 2017. And so the whole goal was to kind of pair students who are interested in seeing mathematics from perhaps a different perspective than what they usually see in the classroom with faculty members that were these kinds of projects. And so going back to fall 2017, I was in the room with like 5 or 6 students, a few I knew, a few I didn't know. And perhaps one of the kind of best mistakes that I think I've made so far in my academic career was just to simply ask them, well, what are you guys interested in studying or mathematizing? And so I made the bold claim that you can just about mathematize any application or anything that you want. And I think back and like, man, depending on what they say, I might not have any type of expertise or knowledge in this area, but no harm, no foul. We will learn. We will learn this together. And so fall 2017 was a busy year with regards to weather. This was right around the time where Hurricane Irma was unleashing its destructive forces right along Florida and the Caribbean islands. And so I remember one student before grad student at a different university mentioned this and was like, well, Terrance, I want to try and mathematize a hurricane. Like, what does that look like? Like, what can you do? What can you study? And so this is kind of where this kind of idea was born. And once again, internally, I was panicking because I was like, I don't know how to mathematize a hurricane. I've never done this before. I've never even thought about doing this before. And so, like, where do you go? Where do you start? What kind of ideas can come from trying to do something with hurricanes? And so, just a couple of quick things before, and I okay, keeping track of time here. So it formed right around August 30th, 2017, dissipated September 14th. I think our first meeting of this group was like September 9th or 10th. And so this is right around the time right after it had made landfall and was one of the most powerful hurricanes on record. Had the highest wind speed of 180 miles an hour, lowest pressure 914 millibars, substantial amount of damage, and the main areas of impact, once again, the Caribbean islands and Florida. Interestingly enough, was the top Google search term globally in 2017. So perhaps I should not have been too shocked that this was on a lot of students' minds. And even though we're all the way up here in Iowa, nonetheless became kind of a fascinating problem to consider. And so okay, the research framework then became, well, how do you mathematize the development of a tropical cyclone? And we spent a lot of time kind of brainstorming, trying to figure out, well, like what does this look like? How does this work? How does this involve, say, different and things of that nature? And so we thought about a lot of different questions, but the one that we really kind of settled on was trying to model what happens after a tropical cyclone makes landfall. And so what kind of assumptions do you make? From those assumptions, what kind of mathematical model can you develop? From that model, can you validate the success or estimate the parameters using data as a tool to kind of influence those decisions? And so we had so a group of students kind of went on the search, and I mentioned that, well, at some point we can make these assumptions. We can think about, what happens kind of from a physical perspective. We can think about what we already know about hurricanes, but at some point, if we do generate or develop any kind of parameters, we're going to have to estimate them, and we're going to need data to do that. And so I think this is being recorded because I have lots of links and all of these different cool, kind of nice repository of data sources that I found throughout the year. One, wonderground.com has a archive of just about every storm, both in the Atlantic and the Pacific Oceans, or in those oceans, I think they're called cyclones, instead of hurricanes. And so we grabbed the data. I had a student that was an environmental science major, and he had some knowledge with GIS software. And so he took each plotted point from and I think there was a corresponding latitude and longitude coordinate in order to try and determine, okay, when did this hurricane make landfall? What was the maximum sustained wind speed? And then from here, we were able to kind of use this data to kind of guide us in estimating the parameters necessary to kind of track or predict what the maximum sustained would be once this hurricane made landfall. This was kind of our starting storm, and then we looked at other storms to help try and determine if what we were doing was making sense. And there were tweaks that we ended up having to make based on the data kind of informing us. Like, for instance, the decay happens a bit slower when you're only partially over land, the tropical cyclone, as opposed to being fully over land. And so there were these things or these kind of considerations that came up that the data kind of help, I guess, kind of tell us or guide us. And so this is when I got really into this whole business of, okay, I can see how, and we do have a data analytics program at Drake, and so I was like, okay, I can see how this could be a really sort of powerful way to kind of help validate and help students kind of understand, if you're mathematizing these kind of real world phenomenon, if there is data that kind of helps support or tell that story, how can we use these bits and pieces of information to tell that story in a way that things are agreeable. And this is, so we kind of took this data, and then like I said, I keep being cognizant of time. The full story is actually told in a SIMIODE publication that I did a couple of years ago. And so if you're interested in running through the same activity with maybe your students, if you teach a differential equation class, I hope that perhaps you'll check this out at some point. And what's cool and what's great about this is that we did this for a couple of different storms, and each year I bring this activity up anytime I teach differential equations, and then whatever is the storm of the month or what's going on in the hurricane season, we do the same thing, and we get really similar results each and every time. And so each class now kind of has a storm that kind of sort of belongs to them as far as their progress or of mathematizing it. And then there are some times where we've added or considered sort of some additional assumptions that come based on the behavior of how the storm is working. And so this was one such example of which we kind of use data to kind of drive the modeling and help support the modeling. And it turns out that, and especially with regards to SIMIODE, there are lots of other kind of problems that kind of either include data or places or resources for which you can obtain the data. And so what I want to kind of now pivot next to is to talk about a couple of current problems that I'm working on with students and where I found the corresponding data source to kind of help support this work. And so here in the next slide, you're thinking about, okay, Terrance, this sounds great, but where do you actually find the data to kind of support or do this work? And there are huge repositories of data kind of all over the place. Given our current worldwide situation, there's of course an increased interest in epidemiology, and data is such a powerful tool to kind of help you determine or predict how certain diseases are going to behave over some period of time. And so I'm working with two students on two kind of separate projects. One tracking hospitalizations in Iowa due to COVID-19. The COVIDtracking.com actually has all of the data for each day, and this might be a little small to see on the left-hand side, you can kind of see where they have, the number of deaths each day, the number of current hospitalizations, the change the number of hospitalizations. And so they're looking at adjusting a kind of typical or standard SIR model to include this kind of compartment for hospitalizations and then the percentage that recovers and percentage that doesn't, and trying to predict at what point, if it will happen, at what point do different policy changes affect whether or not a hospital can potentially become overwhelmed. And so it's a very fascinating project that's taken me down paths that I did not necessarily see myself taking. But it is thanks to this data that we're able to kind of estimate some of the parameters that he's sort of developed or at least hypothesized with respect to doing this. And I have another student who was also interested in epidemiology, but rather than kind of working on COVID-19, she's an international student from Africa. And so they felt the effects and the brunt of the Ebola pandemic much more than we did here in the United States. And so she was interested in looking at different ways in which we've talked about in class with using data to kind of estimate your parameters, different models like either SIR or the SIS model. And so this data.humedata.org actually has several different data sets and all different kind of varieties, depending on what the flavor of modeling that you're interested in doing. And so I found the data set for Ebola cases in 2014 actually starts at 2014, goes up to 2016 that she's currently using, and working on trying to get some decent results with regard to trying to mathematize that pandemic, especially since it's already concluded. And so we can really get a decent snapshot that's kind of trying to mathematize how that happens. A few other projects that I'm working on. I have a student from Ohio who was interested in studying the spread of this of the opiate crisis, which is really, especially over the last several years, really kind of paralyzed communities in Ohio. And so this had a kind of more sort of social justice slant that I was very interested in. And it turns out that the CDC and a lot of these data sets that I've gotten over the last couple of years usually come from government websites. And so NASA has a lot of decent data sets that I've used, especially in like Calculus 3, when we start talking about space and different things from that perspective. The CDC has nice data sets with regards to a lot of different, I guess, kind of crises or epidemics, including the so-called opioid crisis. And so they track the different number of drugs and people that have reported either overdosing, and if they do, where did they do it? What kind of drug did they overdose on? And so they are working on this kind of sort of network. It's kind of a graph theory problem on trying to identify hotspots or hotbeds of places in Ohio where they think this opioid crisis might continue to worsen, and they're doing it based on almost kind of similar to the traveling salesman problem, but kind of an adjustment from that. And so one such place where I found some good data to kind of help support his work. One final one, and then my last like couple of minutes, I will talk about sort of one last, I think, interesting place for which you can find data to help support your work. I have two students in quantitative economics who are interested in looking at the effects of cryptocurrency as it relates to how that could very well change the way that we use money. And then part of their project, they were interested in looking at the different foreign exchange rates because they were trying to find how it affects how one country sort of interacts with another. Once again, this data.humedata.org had a really nice, there's an Excel sheet that they downloaded, and this is a fairly new project, so they're kind of parsing through the data now, plotting it, trying to discern or formulate assumptions and hypotheses based on the behavior of the data. And so we're actually going to meet on Tuesday and see what they have come up with, and then kind of go from there. And so even in economics, there are a lot of nice data sets here to kind of support that work. In the last couple of minutes here before it is my time to conclude, a kind of surprising source of inspiration for which to kind of derive a data set that admittedly I never even thought of. And so I was talking to Brian Winkle once at a conference I was at a few years ago, and he mentioned this activity he did in his differential equation class, which I of course stole, used in my class, and had some varying degrees of success in doing that. And so you, there are some other SIMIODE examples here, and because my time is kind of running low, and I think this is being recorded, so at least I kind of have this out here in case you're interested in looking these up. So spread of technology, there's data taken from, like, for instance, the monthly ebook share of consumer book purchases, trying to understand how technology is how that influences our lives, and the differential equations that you can develop and use data to kind of help either optimize or estimate the parameters associated with it. Another one that I thought was interesting from a sports perspective, and so here's some data that came from Usain Bolt's 2008 Olympic Games, and a lot of the records that he broke with regards to his races. And so someone calculated the different reaction times and compared it to other champion or other Olympic runners. And so a very interesting, I think, application of data analysis and synthesis from SIMIODE, very popular kind of US Census modeling. And they actually updated the population counts all the way to 2010. And then there are different ways, I think, they try and mathematize this particular population growth to try and predict future population changes. And so SIMIODE has a really kind of nice, I think, repository of sort of data-driven modeling exercises that might be of interest to you, depending on what you do with the kinds of students that you work with. But the one that I wanted to kind of briefly mention before it's my time to conclude is that sometimes it's better to kind of develop your own data. And the activity that I kind of borrowed, and by borrowed, I mean definitely stole from Brian Winkle, is that
you got a minute.
About a minute? Okay, great. So then I'm going to tell this very last story here, and then I will conclude at this point. In teaching about Newton's law of cooling, he brought a cup of coffee in, and he had in one of those kind of digital thermometers that you can use to measure the temperature. And every minute or two, someone would measure the temperature of that cup of coffee as it was cooling. And then just like that, you have this set of data points that you can immediately use, kind of validate the assumptions made in Newton's law of cooling, because you can measure the ambient temperature. And we did that, and we put it into MATLAB, and they saw, like, oh my God, Terrance didn't just make up this ODE. It really does kind of match what we expected to see from kind of measuring the temperature of this cup of coffee. And so there are some SIMIODE modeling scenarios for which they do that. They develop their own data. I put these last two here because it is -2 degrees up here in Des Moines. And so, and I'm originally from Alabama, and so I would not mind nice glass of iced tea and Southern barbecue, but I will have to wait for a few months before that happens. In any case, so these are some of the students whose projects I've kind of mentioned, and so I want to acknowledge them and SIMIODE for inviting me to give this talk. And at that point, I will stop here and open up the floor for any questions.
Thank you, Terrance, for a great presentation. Any questions for Terrance? You can unmute yourself or type in the chat window your questions.
I have a question. So when you're having students just come up with their own ideas and sort of running out to all these databases and getting whatever data happens to, tickle their fancy, how do you avoid a situation where the analysis from the student is something like, well, we can see that it increased, or this is bigger than that, sort of like a shallow analysis? Like, how can you be confident that if you're going to pull out a random data set that you're going to be able to find an appropriate kind of sophisticated enough, differential equation or model that will tie into your class material? You see what I mean?
Yeah, I think so. So so if I go back, Because that actually did happen. So we were doing this work with hurricane, and we got this data, and then we plotted it, and I had a student who was a freshman who did not have a ton of experience with like differential equations. We had kind of talked about it, but he looked at this and was like, "Well, Terrance, this just looks like a straight line. Like, how come we just can't use that?" And so one thing that I try and do is, even though these are kind of data-driven type kind of modeling activities, I really try and get them to think about how to develop the model just from their assumptions, and hopefully that these assumptions are kind of rooted in some type of in some type of realism. Like, for instance, we were looking at this one. One of the assumptions is that we assumed that the maximum sustained wind speed decreases at a rate proportional to the zone wind speed. And so the faster the hurricane, or the stronger the wind speed, the faster it decayed. And so that developed a fairly simple kind of separable differential equation. But then after they did that, then we went to the data, and then I plotted the data. It was a decent fit, not a great fit. We estimated those parameters, and then we ended up having to tweak it, because then we realized that, oh, well, it doesn't decay as rapidly at the beginning. Why is that? And it decayed a lot more rapidly than we anticipated towards the end. Why is that? And so then that generated some good discussions that led us to kind of tweak this model. But what I try and do is, rather than them go and find the data first, we develop the model. I find the data set. I hope that the data set will kind of support our ideas. There's been 1 or 2 times where that hasn't happened. And then we go back to the drawing board, and we try and find out, okay, well, what kind of went wrong here? What did we not assume? Do we blame the data? Do we blame ourselves? One, I was kind of successful in resolving. We sort of kind of tweaked the model. The second one was still, I couldn't quite understand, and then admitted that to the students. Like, I don't understand why this data doesn't seem to kind of match up for what we've done and what other people have done. And then, and then at which point I was talking about, well, maybe there's an issue with the data. Maybe,
Terrance, thank you for that answer. I think we have to wrap up this presentation. We got a couple of questions in the chat. Can we get your presentation? I think it's recorded, but the slides, I think the kid is asking for the slides. Could you share your email ID so that people can contact you?
Yeah, I'll do it. And yeah, if you contact me, I can send all of these slides to you, because those are lots of.
Do you want to put your email ID in the chat so that people can contact you? And also that can also help Victoria's question. Victoria, you can see the slide number 15 on the slides itself.
Yeah, Victoria, if you don't mind, if you shoot me an email, I'll just send the whole presentation to you. And that goes out to anybody that's interested in these slides. I'm happy to send that out.
Sure. Thank you so much, Terrance. Let's thank the speaker for this wonderful presentation.